Today we're going to be discussing atoms, ions, and molecules. Starting with atomic structure, basic learning objectives for this chapter are the ability to define matter and list its three forms, describe and differentiate among the subatomic particles that compose atoms, explain the arrangement of elements in the periodic table based on atomic number, diagram the structure of an atom, describe an isotope, explain how radioisotopes differ from other types of isotopes, describe how elements are organized in the periodic table based on the valence electron number, and state the octet rule. All right, that said, matter. Matter has mass and occupies space. Okay? There are three forms of matter. There is solid, liquid, and gas. Solid, as an example, of course, is bone. Liquid is blood, and basically gases, oxygen, and other gases. Okay? An atom is the smallest particle exhibiting chemical properties of an element. And there are 92 naturally occurring elements that make up matter. In the table, you'll notice table of elements, there are more than 92 because there are scientifically manufactured or man-made elements in addition to the natural occurring 92. And there, in this periodic table of elements, the numbers, of course, go, the atomic number, the upper number, goes from 1 all the way, in this case, down to 103. And that's based upon the number of protons in the upper number, basically the name for the element, which is usually the first letter of the name of the element, usually, and then occasionally another letter from its name is also incorporated there, and it could be from its Latin name in some cases, like sodium and potassium. That said, the lower number is its atomic mass, and from its atomic mass and then the proton, we can then determine the number of its overall basis of the balance between the protons and the electrons, which must be in balance. Okay. And of the major elements, there are essentially 6 major elements that are 99% of your body weight. Okay, oxygen is the greatest percentage of your body weight in terms of the elements, 65%. Carbon is 18.5, hydrogen 9.5, nitrogen 3%, calcium 1.5, and phosphorus is 1. And the minor elements, there's still factors, but they're lesser factors. You've probably heard these before too. I'm sure they're familiar to you, whether you recall specific science or not. Sulfur is 0.25% of the body weight, potassium 0.2%, sodium 0.15, chlorine 0.15, magnesium 0.05, and iron 0.006. We don't want to take these numbers as to mean that that's the amount we need to have them in as a percentage of the basis of the body weight in terms of what we ingest. Some people get that confused at times. There's a role there in some of the need for different minerals, among other things, but we don't want to use that as our primary basis for determining what we ingest necessarily, because we're talking about a lot of variable processes and a lot of variable systems at play. It may not be exactly what we're seeing here in terms of actual body weight. And recall that weight, unlike mass, which is really just size, weight is based upon the pull of gravity. Pulling on mass makes it weight. Okay. The components of an atom, they're basically composed of 3 subatomic particles that are part of an atom. Basically, the neutrons and the protons are in the nucleus. The mass of one atomic mass unit is an AMU, or a Dalton, named after the person who basically discovered them or named them, the AMU, the atomic mass unit, back in the early 19th century. There's no charge for neutron, neutral, right? Proton has the mass of 1 AMU, and basically we're talking about a positive charge for a proton, right? Not typically hard to follow that. The electrons, even though the protons and electrons must have the same number, protons being the nucleus, and electrons in the cloud outside the nucleus, or often depicted as a shell, it's the mass of an electron is 1/11800th of the mass of a proton or a neutron. However, they must have the same number to be an atom. To not be an ion, which we'll come to in a little bit here, it has to have the same number of electrons as protons. Okay, neutrons can change, but not protons and electrons in terms of their balance. Okay, that same number, I should say. That said, the electrons are located at varying distance from the nucleus, and those in regions also called orbitals, or in that cloud. Okay. The periodic table of the chemical symbol, which we just looked at, we saw the table and seeing each symbol, and again, it's unique to each element. And the atomic number, as we also mentioned, the number of protons in the atom and element. That's at the upper number in that table above the name or the chemical symbol of the element. And of course, in those rows, it certainly goes from 1 all the way, in this case, to 103. It goes down the row, first row, second row, third row, fourth row, fifth row, and so on. And the average atomic mass, of course, increases as you go down the rows, and that's shown as a lower number below the chemical symbol. As far as the number of subatomic particles, the proton number is the atomic number, okay? Equal to the atomic number, and the neutron number is the atomic mass minus the atomic number, then you get the number of neutrons, okay? And in cases where you see a difference in neutrons, you're not going to see a difference in if it's still an atom. Once again, the proton and the electrons must be the same. You might see a neutron change, which we'll get to in a second here, referring to as an isotope that can vary from each element. It has various isotopes that still have a balance between protons and electrons, but the neutron number can change, okay? Now, in diagramming atomic structures, you have its nucleus here and each shell here. Remember the shell model concept for showing electrons in the orbital or the cloud area here outside the nucleus of the cell here. We're talking about each shell here showing basically the number of electrons. And in this first shell, it can't have more than 2, and each successive orbital, if you will, or shell layer, if you will, can't have more than 8, okay? And that said, the first one, like it's showing here, 2 electrons right there, and again, it can have up to 8, another one outside of here. This is essentially 2, and then you have 6 more. So this one obviously has 8 protons in the nucleus, and it must have, in this case, it has 8 neutrons also in the nucleus, and the outside area has 8 electrons in balance, okay? Now, isotopes, they're different atoms of the same element. Like carbon 12, carbon 13, carbon 14, the same number of protons and electrons, not proteins, protons and electrons, totally different thing. However, the neutrons are going to be higher numbers here, carbon 12 referring to the number of protons and then neutrons here, or the balance of protons, electrons, and then add in the neutrons, really based on protons. And then you have 13 because you have 7 neutrons, and then you have 8, so it keeps going up, and of course the carbon number then goes up. And of course, you'll see additional then, you'll see that the valence here from the standpoint of electrons has not changed here, but you'll see the size of the nucleus is going to be basically growing because the number of neutrons is growing, okay? Identical chemical characteristics between all the different carbons here, but different atomic masses because of the increase in neutrons, okay? And as far as the weighted average of atomic mass for all isotopes, it's the average atomic mass. Radioisotopes contain excess neutrons, what we're just looking at, so they're unstable. Okay, when there are excess neutrons, the more excess neutrons it has over the number of protons and electrons for the normal balance, becomes more and more unstable. And it loses nuclear components from the nucleus, in the form of high energy radiation, which is typically either alpha particles, beta particles, or gamma rays, things you at least heard of before in terms of radiation, right? And the physical half-life of an isotope is basically the time for 50% of the radioisotope to become stable, and that can vary from a few hours to thousands of years, all depending upon the isotope, the element, and its variation in terms of an isotope. The biological half-life is a time required for half the radioactive material from a test to be eliminated from the body. And with some very radioactive isotopes, that can be more than thousands of years, potentially. Okay? That's not normal, but it can be. From a clinical standpoint, medical imaging of the thyroid gland using iodine radioisotopes. The radioisotopes introduced into the body during medical procedures are used by cells in a similar manner to non-radioisotopes, and you can therefore, by having this radioisotope and injecting it, and you can trace the products of metabolic reactions that use those elements. They're tracing, right, to be able to find out what's happening in the body. Pretty impressive stuff. The thyroid gland will then show darker in areas where there's less radioactive iodine taken up, and you can help locate nodules by doing that. Pretty impressive stuff that we can now do. Now that periodic table, when we look at it again here in a moment here, it's not just about the rows, it's also about the columns, okay? As you go left to right, like showing the initial table, we'll go back to in a second here, with hydrogen, lithium, sodium, potassium going down the column. Each of those has 1 electron in their outer shell, okay? And each consecutive column has 1 additional electron. Now it also has another proton, because those have to be in balance, right? So as you go to the right in terms of columns in the periodic table, you still have that balance of the protons and electrons, but they're increasing in atomic mass, they're increasing in the number of protons and thus electrons. But by the time you get to the far side, essentially, we'll go back to this here, we have chemical stable, we essentially have more chemically stable elements and often referred to as chemically inert noble gases. So I'm going to go back here quite a bit here to that table here. So when you have the far right side, all of these rows over here, right? We have this entire column now is going to, or say all these columns over, excuse me. This column here is more chemically stable because, get back here. Oops. Because it has a full valence shell on the outside, full 8, balanced, right? And the more it has less than 8, I should not say the more it has, but when it is a variable from 8 in its outer shell, it has something different than a full shell, that is where there is a greater probability of losing electrons and actually possibly gaining, so it's actually more change that can occur, okay? The potential for more change, or more significant change. That said, elements tend to lose, gain, or share electrons to obtain complete outer shells, right? With 8 electrons, with their basically is where they're the most stable, right? That's known as the octet rule. Other than that first orbital outside the nucleus for the electrons, which is actually just 2 electrons, each successive orbital is going to be 8. Up to 8, I should say, and it could be less than that, which makes it not as stable when there are variants from that full orbital, okay? And again, that's known as the octet rule. So, very short little, or relatively short little quick section here for the first section to get you familiar with, and probably not familiar with, to remind you. This is back looking at CAM again, right? This is not really familiar. This is familiar standpoint. I've gone over it again. What subatomic particles determine the mass of an atom? You should be able to answer that as far as the protons, electrons, neutrons, right? What subatomic particles determine the charge of an atom? Right, positive or negative or neutral. Diagram the atomic structure of chlorine with the atomic number being 17, the mass number is 35, and then showing that nucleus, and then showing that then the electron as far as the valence model of going outward from starting at 2 in that first outer layer, and then with 8 and 8 and so on, okay? And making sure your electrons obviously match up with your protons. Do isotopes represent the same element? The answer, of course, is yes, they do. Do they have the same number of protons, neutrons, or electrons? Neutrons, what's going to be changing, right? And then describing a radioisotope. That radioisotope, of course, they become more and more unstable, okay, when you have that change in that neutron, right? What's the relationship of the octet rule and chemical stability? The octet rule being that the outer layers outside the second layer and beyond of the orbitals outside for the electrons basically has to be balanced. It is balanced when it's at 8. However, each successive orbital that does not have 8 is less and less stable for the greater probability of change occurring. Okay, and we'll go to 2.2 section, or section 2 of chapter 2 in a moment.